This conference will now be recorded.
All right, thank you again for joining us today. I'm really pleased to introduce Henry Barbaro from the Massachusetts Department of Transportation, and he'll be presenting a talk on USGS and state DOT cooperative studies over the years. Since 1993, Henry has served as the supervisor of the Wetlands and Water Resources Unit, as well as the Stormwater Program for the Environmental Services section of the Massachusetts Department of Transportation's Highway Division. During his tenure, Henry has collaborated with USGS on a wide variety of studies with a focus on contaminant loading from highways. These studies have influenced MassDOT's strategies for compliance with state and federal stormwater regulations. Henry has a master's in natural resources planning from the University of Vermont and a bachelor's in environmental science from the University of Massachusetts in Amherst. We thank you for being with us today, Henry. You can go ahead and take it away.
Okay, you can hear me okay?
Yes.
And you see my screen?
Yes.
Thank you, Elena, for excellent introduction. It was a little lark aside here is that my job title has changed a bit over the years. I used to supervise the entire wetland and water resource unit at MassDOT, and we've since differentiated and moved around. So now I think for the past 15 years, I've done only stormwater, the stormwater unit. But anyhow, thank you for inviting me to present, and I really am a big believer in this topic. I think USGS has done excellent work over the past 25 years and has really informed our decision making at Massachusetts Department of Transportation. So the today's presentation, I just would give a little agenda of sorts. I'm going to give background on MassDOT's Stormwater Unit, very brief, and we're going to talk about the 7 collaborative studies since 1997. Talk about the methods and especially the findings of these studies, and also just end it with potential future research and studies going forward. And this is a timeline of the chronological order of these studies, and I just thought that would help. So for those who are familiar with DOTs and how they're set up and their mission and so forth, this might be a little familiar, but so MassDOT is constructing and maintaining its transportation system within DOT. As Elena was saying, we have the Highway Division, and within that is the Environmental Services section, which is broken down into these specialty units, and the Stormwater Unit is one of those units within environmental. What we do, the Stormwater Unit, is we review projects to make sure they comply with both state and federal regulations, and then from MassDOT's perspective, make sure that the measures being used are cost effective and practical. So I'll start with the first study. This was my introduction to U.S. Geological Survey back in 1997, thereabouts. This, and I want to mention too, and Elena mentioned it as well, that these studies pretty much all were driven by environmental regulations on some level, you know, in an effort to comply with environmental regulations. And so in this regard, the Cambridge Water Department had concerns about the I-95 that runs adjacent to one of their main drinking water reservoirs, the Hobbs Brook Reservoir. And I'm assuming you can see my cursor. This is 8 lanes of I-95 running north and south. And so their concern was from our de-icing operations, our winter maintenance, and how it had the effect of elevating salt concentrations in their drinking water. So what USGS did first is that they set up a variety of sampling stations, these sheds you see over to the right, and inside there they had the automatic samplers and the tubes and electricity and so forth. And what's happening here is the USGS employee is calibrating the stream flows and using velocity sensors and so forth. Basically, once the concentrations are taken from the sample bottles within the shed, that translates into, how much loading is the concentrations in the stream reflects the amount of loading to that subbasin to the reservoir. So that's trying to get this closure of measurements. Now, USGS also used flow-weighted sampling. For those that have not been involved in these studies, you don't take just a grab sample here and there. These samples are automatically withdrawn after a certain amount of flow has gone by, and that way throughout the storm, you can get a sense of what was captured at different volumes within that hydrograph, so to speak. Basically, just to get an average loading and concentrations throughout the storm. Okay, so this is a schematic of the watershed for the Cambridge Reservoir, and up at the top right-hand corner is this dark green sub-basin, this drainage area, and that's the drainage area to the shed that I just showed you, and that red triangle is the sampling shed that leads to the reservoir. Now, one of the findings from the study was that looking at the entire watershed, there are lots of other sources of salt, including parking lots and municipal roads, and it's not just this highway, I-95, and a couple others, that is the primary source of salt to the reservoir. And the other finding is that, very logically, that the more impervious area you have, the more salt concentration and loading you're going to have as salt is put down to melt ice, essentially. The next study was done soon after. It was in the late 90s. And this is the cover page of the report. And it shows I-93, the Southeast Expressway going through Boston. It shows one of the sampling sheds on ground level. And the objective here was to determine how some best management practices performed in treating stormwater going from the highway to essentially Boston Harbor or Dorchester Bay. And just in a little aside, not that important, but we called them best management practices until recently. Now we call them stormwater control measures. It's a little bit more of an exact terminology, and but pardon me if I use BMPs and SEMs interchangeably. So you'll see over this aerial photo to the right, you have the 4 different, well, there's a total of 6, but you have these points are the sampling sheds that took samples throughout the study. And you can see the north-south highway and then Dorchester Bay off to the east. Okay, so the methods were interesting. We looked at two water quality inlets. These are underground rectangular concrete boxes. They have these baffles running through them, sort of like a first chamber, second chamber, third chamber, as well as a deep sump catch basin. And what I'm showing you here in part of the methods, we'll talk about this a little later, this static mixer assembly. And the goal here, it's funny. When I was starting out in this business before I was enlightened by Kirk Smith at USGS, who I consider a mad scientist and very smart, that it is critical that the sample you take is well mixed, that it represents the water column from which you are taking this sample. In other words, if you don't mix your sample, where does one put the sample tube intake? So if you put it low at the bottom of the pipe, let's say, then that's great. You get the heavy stuff and the sands and fine sands, but that is not a representative of the whole water column where you have the finer particles, the clays, the colloids at the top of the water column. So in the spirit of removing this sort of sampling error, the bias, Kirk developed this mixer device to create turbulence so that you would have a well-mixed sample when you withdrew the sample to the sample bottle. So we'll talk about that a little bit more later. And then the other thing is that USGS uses SSC, suspended sediment concentration, instead of total suspended solids, because again, there's this, let's say, analytical errors when you are measuring total suspended solids, and you just can't help but, when you're taking sample aliquots, to miss the larger particle sizes, or at least all of them. So that was another, I thought, important point in the spirit of reproducibility and accuracy. So this slide reflects what we kind of went through to take samples and conduct this study. What you're seeing is a couple of manholes to one of the water quality inlets. And again, it's this large concrete box underground. It's not easy to get to. We used confined space entry protocol. We blew fresh air down there, used respirator masks and a harness, and so on. And what we found, one of the findings, is that the sediment there was not a uniform layer of sediment in this box. So this idea that you could look in there and measure with a stick, or even use a vacuum hose, and just sort of stick it into the middle and assume that it's representative of the entire box, underground box, it was not true. You had kind of this drifting into the corners where the sediment depths were much different at the edges of the box versus in the middle. So that was important, because I would say the great majority, if not all, entities that sample and take measurements and clean out these underground chambers, they're just putting the stick or the hose in one location and hoping that they get everything. So you really need to get in there and move things around to do it right. The other finding is that even though these are fairly large chambers, 1,500 gallons, I think the biggest one was 4,500 gallons, and they certainly capture more than your typical catch basin, they still have relatively short residence times. And what that means is that since really there's no filters here, there's no infiltration, it's all based on settling, particle settling. And you need time to settle fine particles. So since these chambers have short residence times, you're only getting the larger size particles. And this is important because the bulk of your contaminants, your nutrients, your metals are on the finer size particles. Okay, moving on here. So again, with these fine particles, you have large surface areas for adsorption. This sort of electrical charges are greater in the finer particle sizes. And overall, when looking at the highway runoff from the South Texas Expressway, 68% of the sediment was less than let's say the sand silt cut off at 63 microns, and 86% was less than the superfine sand size. So what that means basically is that the great bulk of particles in the highway runoff were relatively fine particles, and therefore, that would be your target, to get those finer particles, which these water quality inlets were not that good at. We're not efficient at doing that. So, but at the end of the study, the deep sump catch basin was measured as capturing 39% of the suspended sediment concentrations in the stormwater. And why I have on the slide not 25%, because that's what our state DEP gives us credit for deep sump catch basins, 25% TSS removal. And so it was significant that these catch basins captured quite a bit more than that. And then the water quality inlets captured 32%. But again, it's not really comparing apples and apples, because there was that 32% was after the catch basins. So if you didn't have catch basins, that number would be quite a bit higher. I don't know what it would be, but it would be more than 32%. And it's interesting too, because when our experience is when vendors advertise, oh, hey, here's our new hydrodynamic separator, does all this work, and stormwater treatment, typically their measurements are based on not having an upstream catch basin to capture the real heavy stuff. And so, which is always the configuration. So it's really, you're building in some bias if you don't use deep sump catch basins before you measure the effectiveness of your downstream hydrodynamic separator. The other point here is that we went out there and we did some street sweeping, and we assumed, oh great, we'll see the benefits of street sweeping, but we found that it actually increased the loading for suspended sediment, which seemed really counterintuitive. How can you, if you sweep the streets, how can that increase suspended sediment? So what happened was that these wire brushes of the sweepers, ran into this legacy berms of sand under the guardrail from years and years of winter sanding. And so once they hit those berms, then you had much more sediment basically out there in the street, ready to be mobilized during the rain. So that's why we got that kind of counterintuitive finding. This is a good slide because, like I was saying before, we were challenging some of the findings of these vendors, of these other proprietary devices, let's say, where they would come up with some very unbelievable findings, like 90%, 95% effective at TSS removal and so forth. But when you really dug into their methodology, we found that they were more measuring displacement than they were treatment. In other words, if you look at these slides, what the vendors were doing was on the left. In other words, they took a fully settled and stabilized BMP, underground box, and everything had settled. It hadn't rained for many, many days, and it had clarified through settling. And so your supernatant in the chamber was very clear. And then they measured the storm coming in, the inlet to the chamber. So you can see on the left, it's very muddy, and what was coming out was very clear. And so they said, wow, look at that treatment. But if they just waited a bit longer, like we did in this study, you can see in that slide to the right that the difference was very similar between the inlet and the outlet sediment concentration. That is because that clarified water was pushed out, and now basically the dirty water going in was very similar to the dirty water going out, except for, again, these large particles settling out in the meantime. Let's see. That's good. Yeah, I made that second point too, that deep sound catch basins do capture the bulk of sand-sized particles. Okay, I think I've already hit the first point. The second point, this was really a great idea. Again, that learning experience for me is that the greatest source of error in one of these BMP SCM sampling studies, to ascertain the treatment effectiveness of a BMP, is what is going in the BMP. In other words, you have this muddy solution being conveyed into this box or chamber or basin, what have you. And now, how does one get a representative sample of what's going into the measured BMP SCM? And no matter what you do, even with that fancy mixer device, there's still going to be error. So what USGS did in this study is that they measured what came out, the concentrations of the water coming out of the BMP, which was relatively well mixed and let's say uniform throughout the water column. Plus, they measured what was captured in the BMP. All right, so they essentially dewatered it and measured what was captured, and they backed into what came into the BMP. And again, it is kind of an accuracy quality control check, but they called it the mass balance approach, and it was a great way to correct for sampling bias, particularly in the inflow to the BMP. So that was good. Okay, going to the next study, there was a few years went by, and then MassDOT was trying to address this issue of, well, geez, what are highways contributing, in terms of contaminant loading? And, we were facing these total maximum daily loading reports and these regulatory authorities asking, oh, well, what's this highway project going to contribute to our receiving waters? And there was kind of a trend or a sentiment to conduct individual project-based studies on contaminant loading from each project, and it was just out of the question. These are very expensive studies. So at around that time, Greg Granato was developing his SELDOM model, the stochastic empirical loading and dilution model. And so this had a lot of promise to model this loading, contaminant loading from highway projects, rather than do, a standalone water quality studies. So what we did is we had a statewide study through USGS to collect data at different types of highways, different traffic counts, and we used those numbers, again, different highways, different traffic, different loading concentrations, water samples, to calibrate the SELDOM model. And now that SELDOM model can be used throughout the state to, you put in your parameters, your lat and long and rainfall and stream flow and impervious contributing area and all these parameters. And at the end, you can get a very good idea of the contaminant loading to the receiving water. So that was our that's sort of a summary of why we did that study. And we had these monitoring stations at 12 locations at 8 different highways, again, different average traffic volumes, and we had a couple of interstates, a couple of smaller highways. And here you can see this kind of sampling shed or cabinet with the automated sampler in there, and all the tubes and wires that go with that. And again, we did all this to calibrate the SELDOM model. One of the findings is that, while we're looking throughout the state right now, and I'm assuming into the distant future, MassDOT does very little traction sanding during the winter. We just found that it makes a mess. Sand grains get rounded very quickly. They blow off the highway. So it's just like spreading mud everywhere. So we really don't do that anymore. But back then, there was more road sanding. And the finding was that compared to a highway that was just salted, where there wasn't sanded, that there was significant contaminant loading, particularly nutrients and metals, coming from that traction sanding. And what you see here, what they're doing here is that the slide shows the developing a flow rating curve using water levels and depth sensors and that sort of thing. Yeah, I do have some pictures of this mixer, but it's just so great, I can't get enough of it. So another finding is, you've heard of this NERP data, urban runoff pollutant data, that was taken over some years, many years ago. And for whatever reasons, they were the concentrations that basically were being assigned to Massachusetts highways were much higher than what we found. Particularly cadmium and lead were way less than they were being credited for from this historical data. And the for example, lead, now de-leaded, unleaded gasoline became the norm, and so that probably explains the lead difference, and cadmium, maybe better tire life, and this and that. There's also significant difference between the other constituents: copper, chromium, iron, zinc, phosphorus, nitrogen. So this was an important finding, that basically lowered what would have been the assumed impact to receiving waters. And this is important. And when EPA, DEP developed these total maximum daily loading reports, they were unfairly or unduly assigning waste load allocations to highways and MassDOT than were actually happening. Another finding is that local soils matter, and again, road sands. These are primary sources of phosphorus, and that when you're modeling runoff concentrations, you want to consider soil chemistry and superficial geology. And as far as the pictures here, again, this was all part of calibrating the flows and the automatic sampler, and again, the static mixer was used, and you can see in the bottom right that after going through the mixer, it's so turbulent, everything is very well mixed, and then you have the sample tube withdrawing the sample aliquots to the automated sampler. So this way we're getting the whole range of particle sizes, and it's a much more accurate measurement. Okay, so this slide, that copper and zinc and phthalates were likely coming from tire and brake wear, and then I guess it kind of like salt, that suspended sediment concentrations increase as the impervious area surrounding the highway increases, and traffic volumes and land use should be factored and considered when using or calibrating the Selden model. Okay, this was another study, had to do with catch basin hoods, and it's interesting. It seems like there is so much to learn about catch basin hoods. One thing I've discovered over the years, it seems like they're not used very much elsewhere in the country. I think the idea came from, more sewage treatment than stormwater treatment. But rather than put these everywhere in each of our catch basins, we thought it'd be a good idea to see how effective they were and if they're even worth the effort in installing. So we use 3 different ones. One is called the snout, which is actually glued to the inside of the catch basin. There's a gasket along the edge. The next type of hood is called an eliminator, and that's what you see to the right. It's this is just a plastic hood, and it's it looks simple, but it really is, in my estimation, the best hood that MassDOT could use, because There's no bolts, no gaskets, no glue. You just use friction and you put it into the outfall pipe, and then it has a sleek profile, so it's less likely to get knocked off by a clamshell excavator when you go to clean it. And then it also has this that yellow disc is a clean out if something gets in there and gets clogged. So we found in these findings that the most of the floatables that pass through the grate. Okay, so it's funny when you think about a catch basin, the cast iron grate is actual, it's kind of like a very coarse filter, and it actually keeps a lot of stuff out of the drainage system, out of the catch basin in terms of trash and organic matter. But what does make it through over time, unless you're there to capture it right after a storm or soon thereafter, it becomes neutral buoyant eventually and then kind of sinks and floats around and then gets sucked out of the catch basin anyway. So when it's all said and done, what was captured at the outfall, which is really what this sort of screen mechanism device that USGS uses, it really wasn't that significant, 4 to 10%, something like that. It isn't that they do nothing. It's really like anything, is it worth the expense and the difficulty of installing hoods? Let's see. We looked at the different types of hoods, and we found that certain composite samples, there was not much difference, and that oils and greases and total petroleum hydrocarbons were emulsified in the sump of the catch basin, and so what basically, if there was any oil or grease that got in there, it would just get mixed up and get conveyed outside of the catch basin, just like anything else in the water. So this idea, this theory that there's going to be this layer of hydrocarbons captured by the hood was not what we found. All right, the next study, getting more recent here, is looking at the runoff coming from bridge decks in eastern Massachusetts. This is a cover page. Aesthetically, I love this image. It's the from beneath the Longfellow Bridge in Boston, between Boston and Cambridge, and the water body is the Charles River, and it was taken during the rain, so you can see the scuppers at work as the runoff came, flowed down the scupper to the water. We were unable to, due to the size and length of the bridge, to, put in catch basins or anything like that. Now, the idea was, behind the study was, well, gee, how much phosphorus is actually coming off of bridges? And my assumption was because there are no surrounding soils, this is a standalone isolated bridge, elevated bridge, where could the phosphorus be coming from except maybe, atmospheric deposition or maybe something carried on by car tires or something. But I assumed that phosphorus would be negligible, the phosphorus loading. So that's why we conducted the study, is to try to ascertain the importance of phosphorus treatment for bridges. And looked at 3 different bridges, all state highways, but different sizes and let's say traffic types. One thing I like about this slide is just the ingenuity that USGS had in retrofitting the drainage from these bridges to have it go through the sampling stations so they could, capture runoff samples. And so you can see they hooked into a scupper from the Mass Ave bridge, the Longfellow Bridge, and that's the bottom left. And then on the right is particularly ingenious, where they tapped into a scupper pipe from the bridge, and you can see, this wooden frame. They run it through the ISCO automated sampler, and then they tapped it back into the pipe, and it went on its merry way. So I just thought that was pretty cool. So the findings, in fact, there was some phosphorus coming off these bridges, and more than we thought. And the primary source was the bridge itself, both from the erosion of the surface, of the asphalt surface, as well as the sediment that got on the bridge. Instead of maybe getting blown off like a typical road, blown off into the shoulder, into the grassy edge, it was being retained by these walls and curbs along the bridge. So that what this is showing you is the sediment buildup within the approaches of a bridge here on this Route 20 bridge. So the majority of the sediment was coarse-grained, sands and small gravels. And so this indicates that the actual bridge itself was subject to erosion. And you can see from here, you can see, images of spalling concrete and so forth. So it seems like the moral to the story here is that if you want to reduce sediment loading and phosphorus loading, that you need to stay on top of your bridge maintenance and make sure that the surface is in good shape. Okay, we're down to our second to last study here, and let's see, how are we doing on time? Let me just make sure. Yeah, we're doing okay. Thank you, everybody, for hanging in there and listening to me. I'm trying not to have a monotone, but it's hard. So this study it just sort of wraps so much of what we did the previous, 15 years. It had automated sampler stations, and it employed remote sensors. It also was required by a regulatory authority. The Massachusetts DEP, specified in the study that USGS conduct this study. So I thought that was a great compliment to USGS, and because they know that USGS is the, I don't mean to gush, but is sort of that authoritative source for water quality data and measuring stormwater runoff. So what happened here was we added a lane to I-95 in Wellesley and Needham in Massachusetts. And of course, when you do that, you have even less room along the sides of your highways to install best management practices, stormwater control measures. So based on findings elsewhere in Texas and other parts of the country, the actual performance of a pavement, this open graded friction coarse pavement, in different parts of the country was given credit for the sort of open nature of the pavement, this sort of popcorn pavement with nooks and crannies. That sediment would be trapped in those nooks and crannies. It would not, the way that pavement is built is compiled, it lacks the fines of a standard hot mix asphalt. So you have these voids, these openings, and that sediment would go into these voids. So DOT took full credit for this pavement, and we said, okay, well, we're just going what the literature says, and it says we can take 80% credit for removing 80% of the sediment load from the stormwater. And DEP said, well, not so fast. We want you to do a study. We want you to look at this, and we want USGS to conduct a study. So we had this tremendous advantage in that we had almost all of I-95 in this area anyway is this open graded friction course. But we also had a segment that we maintained as hot mix asphalt. So we had a very comparable controlled experiment here where, it's in the same location, same rainfall, temperature, wind, traffic, everything. And we were very directly able to compare the data. And where the only variable really was the type of pavement. So going to the second bullet, another thing Kirk developed from USGS, which was more mad scientist brilliance, was these dry deposition samplers. And basically the idea was to tease out, to differentiate what was deposited in these trenches. Now, what you can't totally see is this line that runs along, it's newly constructed along the shoulder of the highway is a trench, and that the water runs off to the trench. It goes into a pipe underground, goes to this sort of manhole, which then goes to a sampling station and a weir and everything necessary to measure the flow and the water samples. So how much material going into that trench got there from rain and runoff and wash off from the highway, and how much of it was just blown in there from like nearby dust or dry deposition and so forth. So Kirk developed this device that would open up after no rainfall or runoff was detected. After 6 hours, it would just open up, and then whenever it detected moisture or runoff or discharge, it would close. And that way, you would isolate what was captured during the dry periods, which I thought was very clever. Now, the third bullet, we used a permeameter. That was to measure the void spaces and if there's any kind of compression or the reduction of these voids between the particles of the open grade friction course. And again, we use this hot mix asphalt, almost, literally right next to it, to these, and so the stations were very close together. Now this is, let's see, we talked about the pavement permeability. So that's what we used the permeameter, and there you can see Kirk and Phil where you did lane closures. It was at nighttime. It was very surreal. Taking water measurements at midnight on a highway, but that's basically what it looked like. Water get poured in, and then Kirk would time, would determine the amount of time it would take for the water to fall down this cylinder, hence the measurement of the permeability of the pavement. So this study went on for 3 years, looked at more than 200 runoff events, and not to throw anybody under the bus, but it's just a far more comprehensive study than other ones that have been done, that I was referring to, like in Texas and so forth, where only just a handful of storms were measured. Here's what it looks like from the aerial view. You have the open graded friction course, and you have the contributing area, these kind of purple lines, and then that's the grade. That's the let's say the topography, the grade of the highway, and then in the black lines is the actual drainage area, and the red triangles are the sampling stations. And our preliminary findings, because the report has not come out yet, it's going to probably come out, in the late fall, early winter, is that the open grade friction course exceeds typical pre-treatment BMPs, which typically get credit for 25% sediment removal, and that the sediment coming off of the open grade friction course was consistently lower than that coming off of the hot mix asphalt densely graded part of I-95. So really, both findings were great and somewhat expected, but it was good to see it really run through the rigors of USGS protocol and methodology and quality control. More preliminary findings is that sediment particles were retained in the voids, which I already went through. Increases in the open graded friction course pavement, that it showed that there was some clogging over time, and that it makes sense. It's all conservation of mass there. So if it wasn't in the runoff, it was in the pavement, and then as the pavement filled up with sediment particles, it became less permeable, and less the treatment efficiency went down as well. Okay, now this is kind of a goofy couple of shots. It's sort of to test if you're still awake, and that is the first shot on the left is right when I was asking, or just when I asked Kirk exactly when he was going to publish the final report. And then the shot to the right, I couldn't find Kirk. He was unable to provide an answer to that question. So that's sort of the nerdish water quality joke there. But we are going to use this same site to look at the effectiveness of salting using this pavement as well. So that's a great opportunity. It's great synergy, because one of the problems is when it snows out and these nooks and crannies also fill up with snow and ice, and so the operations people, the plow operators, salters, they feel compelled to hit the pavement with more salt to try to burn out these this sort of look of snow and ice caught in the highway. So we're trying to figure out how necessary it is to do that, and how effective salting actually is for open graded friction pavement. Okay, here's the last study, and it was done by Greg Granato, and he ran a bunch of simulations using the Selden model to see, how different highways and urban runoff behaved throughout southern New England, and his findings were interesting. Now, he measured highways in and around Narragansett Bay, and determined that the nitrogen loading to Narragansett Bay, which is an issue for the ecological health of Narragansett Bay. He found that highways contribute a very small fraction of nitrogen, essentially because it made up a very small footprint of sources of nitrogen in the watershed. And then the other one I thought was a lot more interesting, and that is this whole idea of offsite mitigation for stormwater management and achieving water quality benefits. This is a difficult graph to interpret, and I wish I was better at it, but what it shows is that upstream in a watershed where phosphorus concentrations are low, you can have BMPs can be considered effective, I guess. But as you hit greater concentrations of phosphorus lower in the watershed, it really doesn't matter how many BMPs you use, relatively speaking, because you're just not going to get phosphorus concentrations on a watershed basis. You're not going to lower watershed concentrations because what's in there is in there, and you just can't get it lower. So, and I think, as Greg explained it, it had to do with, BMPs being focused on sediment removal as opposed to phosphorus removal. And so you just do not get much benefit from installing BMPs in the lower half of a watershed. I know it's very generalistic, and I'm sure there are many exceptions, but it opens up that question: is it most effective for the benefit of the entire watershed, the water quality of the entire watershed? Is it money better spent to purchase undeveloped lands in the headwaters of a watershed so that they never get developed and they never have to have BMPs and phosphorus treatment, and it's just simply assimilated as it naturally would be? So I think these findings open up that door, that question. Is it best for DOTs throughout the country to be designing, building, cleaning, these BMPs in perpetuity, forever, and the tax dollars that go with that, versus maybe a one-time charge of purchasing undeveloped land upstream? So I hope I did that justice. It's a tricky one to explain. Now, future research and studies include, like I said, the salt efficiency for de-icing open graded friction course. At what point do you, just because it looks like there's snow in the nooks and crannies does not necessarily mean it's not the friction. You haven't met your friction targets. The second bullet, like I said, preserving headwater parcels. Third bullet, using vacuum sweepers. Like I said, you lose the pavement loses effectiveness over time. So, how effective would vacuum sweepers be? Is it worth the effort to remove sediment in this situation where it's been a bunch of years collecting sediment in this type of pavement? PFAS is become more of an issue, and we really haven't studied that in roadway runoff at all. Looking at how phosphorus is differentiated between total and dissolved in both hot mix asphalt and the open graded friction course. Getting a little fancy, looking at water treatment residuals in bioretention stormwater control measures. It's been happening here and there throughout the country, I've heard about, and it's a way to remove nutrients or phosphorus in these bioretention cells. You know, they're basically like infiltrating swales that typically have a drainage line underneath to where it doesn't infiltrate all the way in. It hits this drainage line and gets conveyed to the outfall. Kind of like a sand filter of sorts. Runoff absorption through vegetated embankments along slopes. That's a good question. What is the water quality performance of SCMs given various maintenance schedules? As a matter of fact, we're dealing with this very thing with catch basins. EPA and DEP want catch basins cleaned after 50%, after they achieve 50% of their depth with sediment. And so presumably due to resuspension, that the water quality performance is going to go way down once a catch basin sump is more than 50% full of sediment. And that's what this bullet is getting at, is like, at what point do you need to clean out an SEM before you have like a marked decrease in treatment? And the last one here is the idea of using urban trees integrated into stormwater design. At this point, these tree filter boxes are tricky because the trees die. They take a fair amount of maintenance and management. And so again, you know, what is their effectiveness? Now, if we have, Elena, how are we doing on time? It's a little past 2. I could take the time to just verbally go through the lessons learned, or people could be just really damn sick of my voice and I should just stop now.
Let's perhaps give people an opportunity to ask a few questions. That might be a good thing to do at this point. I'll go ahead and stop the recording.